Welcome all to this fourth lecture of device materials part of advanced material chemistry course. Yesterday we started solar photovoltaics and we will continue. In last few classes, I wish to summarize that we learned that almost all the practical devices are made using semiconductor materials, and that's why semiconductor materials are important. Then there are two elemental semiconductors which are very important. These are silicon and germanium. And then there are compound semiconductors which are 3,5 and 4,6. These are most commonly used in the practical devices. Then we learned that they are major four building blocks. These are metal semiconductor junctions, PN junctions. There are two different semiconductor heterojunctions and MOS structures, metal oxide semiconductor structures. And any one or combination of these building blocks are utilized in the any working device. You will find working devices which may be having at least one of each building blocks. Then we learned that solar cells are PN junctions based devices, and that converts light into electricity. Important parameters for any solar cells are open circuit voltage, VOC, short circuit current, ISC, and fill factor. And these values, they derive the efficiency of a solar cell. The efficiency of a solar cell depends on these three parameters. Then absorption of incident radiation is very crucial and is very important to select the materials for photovoltaic device where they absorb majority of the radiation. Then after absorption, electron hole pairs are created, and these should be efficiently transported and collected at the electrodes. There should not be recombination. And for maximum absorption of solar spectrum, multiple junctions can also be used, where a high band gap material is high band gap material solar cell is at the top, and just below that we have put a low band gap solar cell material. Then photovoltaic technologies can be categorized into three generations, first, second, and third generations. And in first generation solar cells, mostly single crystalline or polycrystalline materials are used in form of thick wafers. Silicon and gallium arsenide were most commonly used in the first generation solar cells. Then thin film based technologies came into picture, and where a very thin film with very thin film of the active material is utilized for solar cells. So because in you require very less material, and that's what consumption of material was reduced in these solar cells, but efficiency were also less. Amorphous silicon, cadmium telluride, CIGS, etc. were the important solar cells of thin film solar cells category. And these devices are generally having PIN structure. PIN structure means an intrinsic semiconducting thin film is sandwiched between P-type and N-type structures, tech materials. This P and N type of structures, these provide you can say potential, built-in potential, which uh, is used to drive the electron and hole pair or from one place to another place. So they move under this built-in potential. So this is the same like summary. First generation, second generation. Now, today we'll see the third generation or new emerging technologies. So in this third generation, we have organic solar cells, basically organic solar cells uh, called as polymer solar cells. Organic solar cells means where you use organic semiconductor in the solar cell in place of the inorganic semiconductors. So these are organic solar cells, also polymer solar cells, dye sensitized solar cells, perovskite solar cells, and quantum dot solar cells. Uh, Tandem solar cells are when you combine two different kind of solar cells is generally we call tandem. Then these solar cells utilize, as I already said, organic semiconducting materials in place of inorganic semiconducting materials. What are the advantage of organic semiconductor materials? It is number one, inorganic or semiconducting materials are limited. If you see, you can have silicon, you have germanium, and you have similarly the compounds. Second, four, they are all limited, and the fabrication process of organic semiconducting single crystals is very expensive, and uh, there's number is limited. However, in case of organic semiconductors, uh, you have two, one is conjugating polymers or small molecules, and the number is uh, practically unlimited. So the doping cause delocalization of the pi electron in the conjugating material. Conjugating materials is where there are alternating single bond and double bond. So these are some examples of organic semiconductors. If you say small molecules, pentacene, very common, ruberine, and PCBM. In C60 is the this fullerene molecule, and this is derivative of that. And then we have C71 also, C70 also. So there are many molecules of similar structure. These are some common small molecules which are very commonly used in solar cells. And as far as the polymers is concerned, more polyhexylthiophene, uh, polyphenylene, vinylene, and polyfluorine. And there are also so many. These are most common things. So in like this is three hexyl and then polymerized. So it is P3ST, PPB, and PF. Why do we need organic? Because there are issues with the inorganic. Number one, as I said, these are expensive. Number two, you require high purity materials, very high purity materials. And fabrication process is very complex, starting from the crystal preparation to the wafer, then doping, and all those parts are very complex. These are not flexible, and some solar cells use toxic materials, as we saw yesterday, cadmium and selene, H2S, etc. Are these materials are used in the fabrication process. So, can organic solar cell is a possible alternative? Let us see what are the advantage of organic solar cells first. organic materials as such, we cannot say, I'm not talking about solar cells right now. These are low cost, these are good absorber of light. Processing is easy. They can be processed in lab very easily, chemical processing or solution processing. Flexibility, the materials which are made from these small organic materials or organic semiconductors are flexible if they are deposited on the flexible substrate, can cover large surface to area cost effectively because the price is cheaper. So you can have large area coverage. Then there are tunable properties. The materials can be easily tuned where all these uh, chemicals or all these organic molecules which are used as semiconductors by small the alteration in some of the bonds or small chemical reaction, the properties, electronic properties are changed. Then eco-friendly also if biodegradable molecules are chosen. Then what are the challenges? Number one, this is evolving technology. It has not yet matured. A lot of experiments are going on worldwide, but still the technology is in the initial phase or in the mid phase, you can say. It has not yet completely matured. Efficiency of the organic solar cells is relatively low. And there are major issues are regarding degradation and stability of the solar cells. They are the present organic materials which are being used or studied for the solar cells. They are unstable and they degrade very fast in if you put them under atmosphere. And there is batch to batch variation because the materials which are utilized are or they are specific materials prepared for this purpose only. So making in one company or making in the same company, if it is two different batches are prepared, then there's slight variation in the batch to batch variation. Yeah. So, and material purification is difficult. The organic polymers or in small molecules, it is very difficult to purify these. Uh, as far as the difference between inorganic and organic semiconductors is concerned, if you see in inorganic semiconductor, this is a single crystal. Usually, when we talk about the crystalline silicon, this is a single crystal. A long range order where the crystal, every atom faces the same environment throughout the crystal. So there is a long range order, and as a result of that, you have valence band and conduction band, as we saw in the initial classes. And these valence band and conduction bands are uh, throughout the crystal. So once an electron is excited and photon is absorbed and electron and hole pair are generated, these are ballistic throughout the material, throughout the crystal, you can say whatever crystal you are using. So then they are totally free. So inside the material, these electron hole pairs are totally free. However, if you see organic semiconductors, there is no long range order. There are small chunks are there. Though you can call them a polycrystalline, not exactly in a polycrystalline the way we understand polycrystalline in organic inorganic materials. So, so here there's no, because there's no long range order, the bands are localized. So if you have small localized bands there, so these bands are in place of valence band and conduction band, as in organic semiconductors, we call it HOMO and LUMO. And the width is also small. So you have HOMO level, LUMO level, and then there is no continuity. Means up to this, it is one level, then you will have exactly similar level, but there will be a gap, little bit of gap. So electron which is excited from here to here, it since there is no continuity, it cannot move like as it was moving in the inorganic material. So it can hop from one level to another level. So hopping, the process is less probable, so therefore the efficiency, or you can say the movement of the charge carrier or mobility of the charge carriers will be very low. So these are electronically you can say Coulombic bound electron hole pair and called as the exciton. So in inorganic semiconductors, we have electron hole pair, free charge carriers, you can say. However, in the organic semiconductors, we have electron hole pair combined, or there's a bound electron hole pair. This is called as the exciton. Now this exciton has to be separated in order to create an electron hole pair. So how do you separate it? You need a boundary, and at that boundary you require in reaction where the energy is reduced when an exciton is converted into electron hole pair. Let's see how it is done. So just to summarize, organic semiconductor are carbon-based materials possessing semiconductor characteristics. Atoms within an organic semiconductor molecules are bonded by conjugated pi bonds, while molecules are bonded to each other by weak van der Waals forces, as opposed to the giant covalent structure in inorganic semiconductors. So that is a major difference between organic and inorganic semiconductors. In organic semiconductors, HOMO and LUMO are the analogous to valence band and conduction band respectively. However, this HOMO and LUMO are not continuous throughout the material as it was in the case of single crystal, in case of inorganic material. And the width is also very small. So their width is very small means it's a cluster of small molecules which form a small crystal, and corresponding to that crystal there is a corresponding HOMO and LUMO levels. Now if we try to compare, due to this these regions, there is a difference between inorganic and organic. As far as the mobilities are concerned, you see there are low carrier mobilities for organic. It is because of the crystallinity only. So hole mobility is typically 0.01, and if you say slightly bigger clusters or small molecules, molecular crystals, about 20. However, if you try to see in case of silicon, the hole mobility is nearly 500 centimeters square per volt second. Similarly, the electron mobility in organic semiconductors is nearly 0.1 as compared to 1500 centimeters square per volt second for if you try to see it in the silicon material. The carrier diffusion length is typically 100 to 10 nanometer in case of organic semiconductors, and if you try to see in silicon, it is about 300 micron. So this is that is the reason why we in silicon the thickness of the P layer in is typically 300 micron to 300 micron, up to 300 micron. Then carrier lifetime in silicon. about 1 millisecond. In organic, it is of the order of nanosecond in singlet state. However, if you see, there are triplet states are also formed where the spin is 1, and because of the triplet to singlet transition is not allowed, that transition is forbidden. Therefore, the lifetime is higher in this state. Inorganic materials are highly stable compared to organic materials that are generally reactive with atmosphere and show photo-induced degradation. PC preparation, organic, flexible and low pose substrate, room temperature solution processing can be done. So preparation wise, organic semiconductors or you can say organic devices using organic semiconductor is very easy. On the other hand, if you try to prepare using silicon, you need very high temperature furnaces. Suppose you are want to make silicon single crystal, you have to first melt it, and so the processes are very expensive. So if we conclude by that organic have advantages of low cost and easy processing, but uh, we need to further do experiments, or you can say further technology development is required because these materials and the technologies are not fully matured yet. As as we saw in the case of silicon mm, photovoltaic or silicon solar cell, N type and P type were joined together or fused together, and then there were electrodes, ohmic contacts were made to make a solar cell. So if we do a similar kind of thing in case of organic solar cell, organic materials also, so in organic, in place of N, you have acceptor materials. In place of P, you have donor materials. So the materials where you have holes as a majority charge carriers or holes as the main carriers, they are called as donors, and acceptors are where there is electrons in organic material. And then we try to deposit like this, then one transparent conducting oxide. Transparent conducting oxide material is that material which is conductive but at the same time transparent also. These are usually ITO, FTO, such materials. So light passes through this and it reaches at the junction, and then excitons are produced here. Then excitant can be produced here also in donor region, in acceptor region also, and those excitant has to reach at the this interface in order to get separated, and then after that need to be collected at cathode and anode respectively. So this is a structure similar to PN junction solar cell, but there are issues. It doesn't work in the same way as it was working in inorganic PN junction silicon solar cell. So suppose in the energy level diagram, if I try to put the if I try to draw the energy diagram of donor, acceptor, cathode, anode, uh, in case of when they are in the isolated state. So these are energy level for donor. These are HOMO, LUMO of donor. This is HOMO, LUMO of acceptor. This is the level for cathode. Usually used aluminum or 4.3, anode, code, or ITO. You can say ITO is most common from this side. So light also passes. Under under thermal equilibrium, the Fermi level has to align. So the bends like this. Actually, it is not exactly in a same way, but in order to have a better understanding, uh, we have symmetrically bent all the you can say bands for the donor and acceptor, and this is the thickness of donor, this is the thickness of acceptor, and this is the connection. So if light falls, in that case, the photon is absorbed and we see an electron and hole pair is uh, generated. So this electron hole pair is at this moment, it is a bound electron hole pair and called as exciton. Now you see this electron hole pair, since it is bound, there's net charge is 0. So though there is a, you can say there is a field or electric field, but since the net charge is 0, it will not see the, the, the exciton will not move because of the gradient in the field. So it will move statistically. So the first problem is this. When it can move in any of the 4 pi directions, this exciton, so moving towards this junction is probability is very low. So let us imagine in a situation, the most conducive situation where the exciton has moved to junction. Now this energy difference, this energy difference between anode and or you can say donors LUMO and acceptor LUMO. So this, if electron moves from this place to this place, this will be energetically favorable. So therefore, the exciton will break. By breaking this, the total energy of the system will be reduced, and therefore this kind of you can say dissociation is favorable. But for in order to dissociate, it has to first move to the boundary where donor and acceptors are meeting. Once it has reached, it has dissociated. In that case, now this electron sees this gradient, field gradient. Similarly, the hole also see this field gradient. Hole and electron moves opposite, and they moves towards cathode and anode and collected at the respective electrodes. So now you see how many problems are there. First is the electron hole pair, which is not actually created as an electron hole pair, but it was created as an exciton. So exciton, if electron and hole pair, they are bound in the bound state, it's a very highly probable that they will recombine. So recombination is most probable. If they have not recombined, then they can move in any of the directions because they are actually charge neutral, so they will not necessarily be moving in this direction. In so out of so many excitons, some exciton will move, only some excitons will be moving towards this direction where they will see the junction, and at the junction the electron hole pair will get separated and excited by after exciton is dissociated, and then once they are separated electron hole pair, then they can move. So if we see the in a broader, you can say picture, same thing. Here you are having an acceptor layer. Here you are having a donor layer. There is a one electrode. There is another electrode, and suppose your radiation is falling somewhere here. So electron hole pair will be generated. Exciton will be generated, but this exciton will recombine before it reach anywhere. So we see this area and this area. Whatever excitons are created, all of them are lost because of the recombination. And only to a very small part where the electron and hole pair are separated by only this distance. They can reach to the boundary and then they can get dissociated and form electron and hole pair, and then they can move here and here. So this distance is called as diffusion length. In typically polymer solar cells, this is of the range of 20 nanometer. So in case suppose you have deposited a blend of 50 nanometer and 50 nanometer bilayer donor layer 50 nanometer and 50 nanometer acceptor layer. So only 10 nanometer will be an active layer. All this will remain whatever carriers are generated here, they will get recombined. So that is the reason why this double layer has a very low efficiency. So typical efficiency of such solar cells are less than 1%. 1% is also when you optimize all other things and this optimize all other things in a perfect way, and this thickness are also very less. So if we cannot increase exciton diffusion length, what we should do actually, ideally the exciton diffusion length should be equal to the length of or you can say total length of the or total thickness of the active layer. But in that case, if thickness is if you keep thickness only about 20 nanometer, in that case, as we saw yesterday, there is another parameter that is thickness. If thickness is less, then absorption will be very low. So the radiation which is falling on that solar cell will not be absorbed. So if we cannot increase the exciton diffusion length, then can we try to bring junctions nearer? Is it possible? Can we do it? Yes, we can do it by a method called as the you can say where a blend of donor and acceptor is prepared. Blend means you just mix both donor and acceptor by blending them together. So now in this situation, there are no two different layers like that was the case in case of silicon solar cell. However, you have a blend of donor and acceptor. So suppose this is your donor and this is your acceptor. So you can have this kind of structure. So you are having here you are having acceptor, here you are having donor. These are all means it can be like anything. You have just mixed it. So structure can be of any type. And this total thickness is still remain 100. But at this time, now what we see, we have actually increased the area of the boundary of donor and acceptor. So you see earlier the area was only this much. This you can say how much was the area? You just this length multiplied by whatever was its width. Now the area of junction has increased. So now in case of anywhere, suppose you see here at this point a photon falls and exciton is generated. So rather than moving from this to this point, earlier it was here at the center, it can move to any nearest boundary. Suppose it can move here also. So it moves here. Now at this boundary, electron and hole pair will be separated, and this electron will move towards this through this material, acceptor material or a donor material, and here the hole will move through this donor material and electron will move through acceptor material, and it will go to the electrode. So same thing is shown here. So these are electrodes, and hole move in this through this white material, and electron moves through this gray material. Now, so you need to increase the contact area of uh, contact area between donor and acceptor. So what is the ideal situation? Ideal situation will be like, ideal structure will be like this. If you make electron, you can say acceptor structure like this and donor like this, and then you will have the maximum boundary area between the, or you can say maximum surface area, coverage area between donor and acceptor. Let us see the same structure. This is theoretical, but practically this kind of structures can be made like this. And so here you have an electron conductor, here you have an hole conductor, and there is an active layer blend. Active layer blend means this is a blend of electron hole, the blend of donor and acceptor. So this is not one material, it is actually an active layer, which is a blend of donor and acceptor. So now suppose light falls, in that case electrons and hole pairs will be generated. These electron holes will be moved towards this, and they will be collected through a hole conductor, and similarly the electrons will be collected by this material, which is a electron conductor. So we need to select then electron or hole selective contacts. Similarly, the material which we are using here, it should be, so suppose this material which is a hole conductor, the material should have properties that it should not conduct electrons. Similarly, a material which is conducting electrons, it should not conduct the holes. So the material selection of hole conducting or hole or electron conducting is also a very important field, and these materials are called as HTL or hole transport layer, where the holes are transported but electrons are blocked. Similarly, the materials where electrons are transported and holes are blocked are called as the electron transporting materials or ETL. So this material we can say ETL, this material we can say HTL. And how do we select it? We select it depending upon the energy levels. So suppose we find a material which is also an organic material, and this is having the uh, valence, or you can say HOMO and LUMO, because we are talking about in organic, we are talking about HOMO and LUMO here. So suppose you have EV here, this is the active layer material, this is this color is active layer material, and you in one side you have put one material which is having energy levels EV and EC here, and on the other side you have put materials which is having energy levels EV and EV these. So if you see, if hole and electron and holes are created in this material, the electron will be easily transported because there is another electronic level available here. So electron can go here, but electron cannot move this side. So because here it has to, it need a lot of energy in order to go from here to here. So this electron can move through this easily. So, and so this part, this material will be actually electron transporting material, but at the same time, hole blocking material, because hole will not move from this point to this point. Now here, hole can move because this is the level which is very close to the energy level of hole energy. So this will move toward this side. However, the whole here cannot move from this to this because it requires a lot of energy to move from this side to this side. So here this material we can say it is a hole selective material or hole transporting material which can easily transport hole but cannot transport the electrons. That is not possible because you require more energy. Similarly, this material will be now, it will block the hole transport, but at the same time it will facilitate the transport of electrons. So this way the materials are now hole transporting material and electron transporting materials are utilized. So what are the advantages of this is number one, high surface area for these nanostructures in nanostructure in bulk heterojunction mode. And we allow the use of locally thin absorbers because you have placed a very, very thin absorber, which is actually a blend of what both donor and acceptor. And but problem is that this thickness which you are putting, it is, though it looks here that we have placed a perfect thickness layer over the electron transporting material or between the hole transporting electron, but controlling this thickness at such a small level when the total thickness is nearly 20 to 30 nanometer, it is very, very difficult. So you will have many pinholes, the thickness control will not be perfect, and therefore the quality will be of very poor. Imagine a very, you can say small, so you are trying to deposit this layer and a very small part here, this is missing. So now what will happen? This yellow, you can say material will come into contact with this blue material. Now this will short, this will simply short this contact. So in that case, this your entire you can say mechanism will fail and the solar cell will not work because it will become short. So that is a very big problem in the fabrication process. So similar to like silicon solar cell, we can see what are the different loss processes in the organic or polymer solar cells right now. So if sunlight falls, if sunlight is reflected, that is a loss. If it is coupled to the solar cell, very good. But if the photon is not absorbed and it passes through, then it is a loss. Now let us imagine the photon is not passed through, but it has been absorbed. Then after absorption, what will happen? There will be exciton will be created. And now the exciton is created. We have seen that this exciton has to move a lot before it gets separated. So if exciton recombine, that is a big loss. But so if exciton is not recombined, then how electron or hole are created? They are free charges. Now, once these free charges are created, they can also recombine. They can back recombination is also possible. So that is also a loss. If that is somehow we can manage, so then finally the electron and holes are separated by the this built-in field, and they are collected at the electrodes. If they do not recombine. So finally, so you see so many losses which are highly probable. All these losses needs to be minimized. So if we see in terms of quantum efficiency, what is quantum efficiency? If we define quantum efficiency, a single photon which is falling a particular wavelength. So quantum efficiency is the ratio of number of carriers collected by the solar cells to the number of photons of a given energy incident on the solar cell. So suppose a particular photon is falling, how much, suppose 100 photons is falling, then how much fraction of photons are giving you the respective electron hole pairs which are collected at the electrodes. So ideally it should be one, but then it is calculated that you have more number of photons of a particular wavelength. They are allowed to fall on the solar cell, and the current is measured in the short circuit condition. So the total quantum efficiency, that is external quantum efficiency, is equal to optical efficiency. Optical efficiency means, as we see, all these things, all these are accounted in this equation. So optical efficiency means if it is not reflected back. Then light absorption efficiency is the probability of absorption. Similarly, this all. One by one, we will see each of these. I have put one slide for each of these parameters. And there's one thing, it is external quantum efficiency and internal quantum efficiency. So internal quantum efficiency is when I have taken care of the reflection of the electrons also. In that case, it will be considered as the internal quantum efficiency. So now, first let us see light absorption efficiency. When a photon falls any material, if it was inorganic material, the photon, if the energy of the photon is higher than the band gap, then it will be 100% absorbed, because above it is continuum. But in case of organic materials, as we saw, the HOMO and LUMO has certain width, and therefore it is not like that all the amount of radiation will be absorbed. And in place of a step kind of function, like there it was a step kind of function. So suppose energy wavelength is above 500 nanometer, or say in case of silicon it was 1100. So up to this it was totally, you can say, passed, and below this it was totally absorbed. But it is not the case of organic semiconductor. In organic semiconductor, we have such kind of peaks. So this is the absorption spectrum for like P3ST material, which is a polymer used in the polymer solar cells most commonly. Then you have PCBM, which is an acceptor. This is the this one is the absorption spectrum of the PCBM, and this is spectrum for the other materials. So and this dotted spectrum is the solar spectrum, the corresponding solar spectrum. So if we have this P3ST material, which is I'm using as a donor material, so this can absorb only this part of the spectrum. All other part will anyway go waste. So if this part is not absorbed, this is waste. So the efficiency is obviously going to be very low, because you are able to absorb only a small fraction of the radiation. So this is the one thing. So we can think that if we use a very low band gap material, and we increase the thickness slightly more, then will it solve our problem? As we discussed the case yesterday, no, it will not solve our problem, because what happens, if you consider the donor acceptor levels, HOMO-LUMO levels here, the open circuit voltage of a solar cell, which actually depends on the difference of HOMO level of the donor to the LUMO level of the acceptor. This difference, it defines how much is the voltage will be built-in potential, you can say, or the open circuit voltage of the solar cell, of the polymer solar cell. So suppose now you try to reduce the band gap. If you try to reduce it as low as possible, so what will happen? This will come very close to each other. So what you will effectively lose? You will lose the voltage. If you will lose the voltage, and though this will move, the electrons and holes will move, but the current, you can increase the current, but the voltage is less. So this will not serve the purpose, and then you will have more heat losses here, and there will be a loss of electron transfer. So therefore, you can say reducing the band gap is not the solution. What are the other important things? Is the excitant movement, or you can say excitant dissociation. So if you see time scale, when an photon falls and electron hole pair is separated, exciton is created, you see the time scale, which is actually very less. It is on the femtosecond level, femtosecond scale. However, this recombination loss, you can say recombination where this exciton it combined back to the this electron combined back with the hole and emit a radiation. This is having nanoscale, mm, nanosecond scale, and the back transfer. As I said, the electron can recombine through back transfer also. The time scale is of microsecond level. So you need to take account all these things in order to how much is the photoluminescence uh, emitting out of your material, how much is the back transfer recombination probability, and how much is the charge separation states. So by doing this, all that, the by you can say combining all these processes, finally the ratio of number of electrons reaching interface, where it is the interface, this interface. So before they reach the interface and do not recombine, to the total number of excitons created, it gives you the excitant dissociation efficiency. So this is excitant dissociation efficiency is only for this part. This is for these two are for like recombination, loss of recombination. So we can see the recombination probability, and here also the back transfer recombination probability. These things and these things they combine, and actually we can make all of these three together, and because directly measuring the number of electron hole pair generated at the interface is very difficult in case of polymer solar cells, and therefore all the three has to be looked in the you can say totality. Next comes the charge transfer efficiency. The electrons and holes drift towards electrodes. On the way, they may also get trapped in some energy, you can say trapped levels, some impurity levels, or they may get recombined also. There, that is, this recombination is different than the recombination which was taking place with the whole value, with the whole of the original hole which was created. So that is the ratio of total charge reaching electrode to the total conducting charge created at the interface. It defines the charge transfer efficiency. So So by doing this, now we have understood the efficiency, how the efficiency is actually getting affected due to all these processes. Now let us learn little bit about the materials. So number one, what is that? Uh, transport transparent ohmic contact on substrate for holes. So what are these materials? These materials are usually ITO and FTO materials. FTO is thermally more stable but has higher sheet resistance and somewhat lower transmission. Aluminum doped zinc oxide is also an option, but it is not very commonly used. FTO is these most common materials are ITO and FTO. These are transparent material, but at the same time conducting also. For the active layers, donor materials, P3ST, it is being used for last nearly 20 years. And these are short names of MD, MO, PPB, P3ST, and then there are metal thiocyanines, then PCPTB, PCPD, TBT, PTB7, etc. These are the donor. These are polymers. The short form of the polymers. There is a big, the organic compound, big compound name is written normally in the shorter form. For acceptors, N-type materials, we have perylines, fullerenes, PCBM, PCBM where this is C70 and some other fullerene derivatives. Small molecules are also used. Then electron transport, hole blocking layers. Most commonly used is lithium fluoride and zinc doped tin oxide, titanium oxide, and this organic material. For hole transport materials, the commonly used materials are P dot PSS, molybdenum oxide, vanadium oxide, nickel oxide, tungsten oxide, etc. Small, very thin layers. These the whole transporting layers are of very lower thickness as compared to the active layer thickness. And then back contacts are aluminium, gold, or calcium or silver. Back contacts means the contacts which from where a means the current is drawn or power is drawn from the solar cell. One is this, and the another is from the top side is ITO or FTO. And what are the fabrication techniques? How do we fabricate? These are physical vapor deposition. Physical vapor deposition means a material is taken inside a crucible and the temperature is raised, and then afterwards the once the temperature is raised and it is inside a vacuum, it's kept inside a vacuum, so it will evaporate, and after evaporation it will go and deposit on the substrate. So this process is physical vapor deposition. Then chemical deposition is also by LB method or CVD method. Material can be deposited. Then there are solution techniques. These are spin casting. You have material and then there is a substrate. You are rotating the substrate with a very high speed and put a small drop of the material which you want to deposit, and then it will smoothly over the surface it will be deposited. Then doctor blading is a similar method where some can say tool is used to spread over the surface and then self-assembly spray, etc. These are the general fabrication techniques, deposition techniques. Then what are the current problems in bulk heterojunction solar cells is number one, small absorption width of the known materials. So the to find out the materials which have which can absorb more, and the efficiency is lower. Obviously, the efficiency need to be improved. The typical efficiency nowadays is about 12% on the very few experimental devices. But the common polymer solar cells, the efficiencies are between 6 to 8%. And the another big problem is that solar cells made from the organic molecules or polymer solar cells have a very short life. They can within a few days, sometimes within week, they actually degrade. So lot of experiments are being done in order to find out the new materials which are suitable, which are stable also, uh, which can be utilized in the solar cells. So just to summarize these things, active layer, heterojunction mixture of donor and acceptor material. This is an active layer, which is a heterogeneous mixture of, this is, suppose this material is donor, this is acceptor. So you have just blended, and this so that uh, each interface is within the exciton diffusion length of nearly 10 nanometers. So every suppose a exciton is generated here, so within 10 nanometer it should see an interface where it can uh, dissociate from exciton to the electron hole pair. Then overall active layer thickness, this thickness, if you see total thickness of inside a bulk heterojunction is, this total thickness is nearly 100 nanometer. So that the total light which is falling can be absorbed. It doesn't absorb the 100%, but the maximum light can be absorbed in the 100 nanometer range. If you try to increase the thickness beyond 100 nanometer, in that case, this process of or you can say probability of donor and acceptor touching the link from donor and acceptor touching the respective electrodes become very less, and therefore it will start behaving like a bilayer solar cell, bilayer organic solar cell. Then a highly conducting hole transport and electron blocking layer of P dot PSS is so this was like a general organic solar cell. When you add a P dot PSS layer or a hole transport layer and an electron transport layer, in that case you can have an improved performance. So this is an electron transport layer where, as we discussed 3-4 slides ago, there is a level which only transport in this through this layer, only electron can transport from the active layer to aluminum, and through this P dot PSS layer, only holes can transport from active layer to the ITO, and electron will be blocked. So this is electron blocking hole transport layer. Similarly, it is electron transport hole blocking layer. So now we can see a total bulk heterojunction solar cell where ITO over ITO, there is a P dot PSS layer. Above that, there is an active layer, and above that, you have a lithium fluoride whole electron transport layer, and above that, you have an electrode, and then you can make a connection. And when light falls on this active layer, the current will flow through this circuit. So, how it is made inside laboratories? So, first, the film is patterned by wet chemical etching. Then whole transport layer is spin coated uh, over that, and then it is treated at 120 degrees centigrade, because P dot PSS has little bit of the water component. Then the active layer of donor and acceptor material is which is prepared by blending in 1:1 weight ratio of P3HT and PCBM. PCBM is, as I said, P3HT is a polymer, PCBM is a molecule, small molecule. This is donor, this is acceptor. So you take 20 milligram per ml P3HT, you take 20 milligram per ml PCBM, you blend them and mix them, you can say in dichlorobenzene, and then stir them for nearly 2 weeks. After 2 weeks, you get a very good blend. This blend you can deposit using a spin coating on the layer which you have already deposited, whole transport layer. So on whole transport layer, then you deposit this blend, which you have prepared by blending for 2 continuous weeks under dark inside a globe box. Then after that, this is given a heat treatment of treatment up to 130 degrees centigrade for 3 hours. And then aluminum contacts are deposited using shadow masking. Shadow masking is a thermal evaporation technique where some blockage is used or you can say some mask is used for getting a contact of appropriate dimensions. In animation, I can just show these processes one by one, step by step. So suppose this is a glass. So, and it is a ITO coated glass we get from the market. This is a glass over this. So it is now ITO coated glass. By chemical etching, so how do we do chemical etching? You put some strips and dip it inside the acid, appropriate chemical, which include acid also. So what happens? That acid, the masking part is because it is not exposed to the acid, so or chemical, so it will not be dissolved. But the part which was not covered will be dissolved through acid, and therefore you will get such kind of pattern structure. Over that, the whole transport layer of P dot PSS is deposited by spin coating, and then after that active layer deposited by again spin coating, and you see the thickness of active layer is slightly higher as compared to the P dot PSS. Then an electron transport layer of lithium fluoride is deposited by thermal evaporation, and then this one is deposited by again by spin coating only. The electrodes are deposited by thermal evaporation. Now you have two electrodes. One is this ITO and another is this aluminum. So, and now you can see there are 9 devices, 1, 2, 3, and this is 3. So this is a matrix, 3 by 3 matrix. So you will have 9 devices, and you can select any device by selecting the contacts appropriately. Now you put suppose an contacts wires here, because this is aluminum, you can have a direct contact here. Similarly, ITO also you can make contact with the gold deposition and the with a gold wire. Then the exciton is first created, and suppose this exciton is dissociated. In that case, electron hole pair are separated, and this moves through an external circuit to give a current. These are some of the photographs. So this is for the patterning process. You have this is a glass substrate, and over that there is a ITO. So you can see it is looking like a transparent, though it is conducting. So this side you have ITO. Over that you put certain strips, and then after that this is a spin coating system. So there you place this after the etching. And then this you just put a drop here, and then this is rotating with a very high speed. Here also you can see it is rotating and active layer deposition. Over that, the active layer is depositing. Then this is the masking. So you have certain, they can say open area here, there, and then you will put this part here. You see somebody is putting it here, and then afterwards just close this completely with some wires, and then you can have the aluminum deposit other side, and then this is the final device. This is the final device for IV characterization. Now you have one electrode here, you have another electrode here, and then illuminate this device with light, and then measure the current, voltage current characteristics here. These are the devices made in our laboratory. This is a flexible 2" by 2" polymer solar cell. This is also flexible solar module where certain solar cells are, these are the individual, you can say, pixels of the solar cell. These are in series. Then this is in one module, which total in series. This is in series. 9 devices. These 9 devices are in series, and then these are in the parallel. So overall, if you add, we have got 15 volt, 3 milliampere power supply. So this is can be this is just for showing the practical application, like how a solar cell can be fabricated. The structure becomes like this. You have aluminum top contact, you have PET substrate, and above that PET substrate you have P dot PSS as a contact also, and whole transport layer also, and then above that active layer. In this flexible, the electron transport layer was not used. So the efficiency was low, but some things has to be compromised for making many things. So this was the polymer solar cells. Now let us come to dye sensitized solar cells. So dye sensitized solar cells differ from the conventional organic solar cells in a way that a dye is used for the initial absorption of the sunlight. In polymer solar cells, what was used in organic solar cell, the light was absorbed in both donor and acceptor things. Here, there is a dye. Dye is a, you can say, color is used for initial absorption of the sunlight, and after that once dye has absorbed the radiation, the dye will become excited, and the electrons will be extracted from the valence band, and the hole will be extracted from the conduction band, or LUMO, you can say, HOMO or LUMO, and they will be utilized to generate the photovoltaic effect. So a dye differs from semiconductor absorber for bulk heterojunction, and it only performs the absorption function and generally has no role in the transport. So in polymers, the semiconductors were, the transport was also happening through those only. So because in this DSSCs, the dye is used only for the purpose of absorption, and therefore it is often referred as a sensitizer. In the dye semiconductor solar cell configuration, dye semiconductor means dye is sensitizer, and then near to that sensitizer another one semiconductor is placed. That is usually TiO2 in most common applications. So that dye is sensitizer. It absorbs, exciton, it is excited, the electrons are immediately collected by this semiconductor TiO2. The dye is present in a monolayer on the semiconductor surface, so that charge from dye may be easily transferred to the semiconductor. So you have a semiconductor, TiO2 semiconductor, over this dye is in a monolayer form. So dye is very thin. Light falls on the dye, it gets excited, and then electron is immediately transported to the semiconductor. So in conventional DSSC, electrolyte with ion conduction instead of electrons is used for regeneration of the die. Eh, uh, So it is like this. A glass, over that you have a FTO layer. So light will come from this to this side, and above that you have actually put a semiconductor which is TiO2. Over that semiconductor you have placed a die. So you consider this TiO2, the TiO2 you have just dipped inside the die. So over this entire, all these big balls, the die will be attached. Now when light falls on these, the die get excited, and this electron is collected by the die molecule, or the semiconductor, and this hole is extracted from this redox. So we have uh, lithium iodide and I2 mixture, which creates a redox couple, which is giving you with, for like completing this circuit. So a monolayer of dye is coated over nanostructures TiO2 to increase the absorption area. Organic dye absorb photons and transfer electrons to TiO2. This lithium iodide and I2. Iodine mixture of lithium iodide and I2 is these are mixed. These are put in a acetonized organic solvent, and then this can use as a redox couple. So the oxidized dye molecule is reduced to the original state by supply of electron through the reaction. So what is there? So in this you have 3I minus, the I3 and 3I minus. So you have what you have put actually lithium iodide. What it gives? It gives you lithium plus I minus. And you have I2 here. So now you have I2 plus I minus. This is from here 3I minus plus 2 electron. It gives you I3 minus. And at the counter electrode here at the platinum, what happens, what reaction takes place is the I3, which takes 2 electrons from here and again get converted into 3I. So you have 3I, which takes 2 electrons from here, it gives 2 electrons to die, it gives 2 electrons to die and becomes I3 minus. That I3 minus again take electrons from the platinum counter electrode and become 3I. So the reaction, it remains 3I. However, in the process, it has transported the electrons. The current in electrolyte is ionic, whereas conventional organic solar cell is electronic. Clear? So dye sensitized solar cells shows efficiency of nearly 13%, and it is stagnated for so many years. The efficiency is because the dyes are also fixed nowadays. The semiconductor is also fixed. This is also fixed. This is also fixed. You are using platinum and FTO as a counter electrode. You are using FTO and then TiO2 as so all the process have been optimized many years ago, and so there are no chance of further improvement unless you change to some new dye, or if you try to change into a new dye, then you need to find out an appropriate semiconductor also. So there are many things. If you change one thing, you have to change all of the things. So you have to find all the this redox material also is having appropriate energy levels which suits with the energy levels of the die if you are trying to change the die. So you have these 4 components only, and you can play with, you can change and try to improve. So light enters through transparent FTO. This I have already explained. From here it goes like this. Light entered through transparent FTO coated uh, uh, chlorine coated tin oxide, and then this excited electron is into TiO2 conduction band, then electron diffused to transport to anode, dye molecules goes like this. And I have an animation, so it will give you a more, you can say, clear picture. So this was glass substrate, and now it is FTO coated glass substrate, which is purchased from the market. Then over that, a TiO2, a compact TiO2 layer is deposited so that it makes a very good contact with the FTO. And then over that, the TiO2 nanoparticles are deposited. Now this entire, you can say, assembly is called as the photoanode. Now after that, a heat treatment is given with a, you can say, with a predefined program. And after that, you deposit this, you try to deposit dye. And how you deposit dye? You dip it in a prepared dye solution. So after dipping for some predefined time, you get this kind of structure where on these nanoparticles, dye molecules are a very thin layer or monolayer of the dye is deposited over the TiO2 nanoparticles. This process is called as dye loading. Dye loading means loading of dye over the semiconductor particles. Now, after that, a counter electrode is bring. What is that? That is also actually a thin platinum layer is deposited over the FTO coated glass. So FTO glass over with a thin platinum. So you have a platinum counter electrode now, and this entire thing is assembly is sealed. These are actually, there's not much difference here. They are very close to each other. Then the external circuit is made by connecting this platinum through this wire, and similarly here with the FTO, which is a conducting one, through the another this. You have a load and you have current meter and voltmeter place. Voltmeter you can put parallel to this. And then, so suppose this energy level of this dye are like this, and this is the solution of lithium iodide plus I2, which becomes like lithium plus I, and this I2 and this I minus, they becomes I3 minus. So this is like I3 minus and then 3I. It keep on, you can say, regenerating each other. Now let us see when light falls, what happens. So this dye is excited. The electron is reached here. This electron is immediately collected by this semiconductor, and then these semiconductors are interconnected. It goes to this TiO2, the compact layer, and then immediately it is collected by the FTO, and after the FTO, it goes like this and then comes here. In the same time, in the meantime, if you see the hole which was actually left here because of this electron, this was regenerated by taking one electron from this I3 minus. If you take one electron from this I3 minus, it will become I3, 3I minus. So it will get converted into I minus. So then this will be, now this will become I minus. So this I3 minus will take one electron. This I3 minus will take electron from here actually, and then it will get converted into 3I minus. So let us see it once again, so that you see this electron is going from here to here. Similarly, this electron is coming from here to here, and this electron is coming from here, and actually I3 minus converts into 3I minus. This it is not collect. This is not actually collected by I minus, but this electron, after collecting the connecting the electron, the I3 becomes 3I minus. Similarly, after collecting the electron, this becomes I3. Just see once again, so you will not forget it again. So this was the working of ESSC. Now, characteristic of this semiconductor and die, TiO2 is preferred as it is relatively inert, cheap, and has low recombination of the charge carriers. TiO2 has 20 to 30 nanometer particles and band gap of 3.2 electron volt. So if you see 3 electron volt, where it falls? It falls in the semiconductor region only. And it is N-type due to the oxygen vacancies and has typical thickness of 100 micron. So now this TiO2, the compact layer is sintered to provide good contacts between the particles. The transport of carrier in TiO2 occurs by diffusion. Diffusion length of the carrier should be larger than the thickness of the oxide. It is obvious in order to get the transport. So carrier in conduction band of TiO2 may be lost due to reducing I3 minus by reaction I3 minus plus 2 electron which is taken from the conduction band. I minus. Now what are the so this is one die. Most of these dyes are ruthenium based dyes. What are the good characteristics for a good dye? These should have good absorption and metal oxide surface. There should be significant overlap with the solar spectrum so that more spectrum can be absorbed, and then fast kinetics of electron injection of TiO2 compared to recombination of the dye. See, it is also possible that once after absorption of radiation, electron hole can recombine back. So before they recombine, they should be collected by the TiO2. So the kinetics of electron injection to TiO2 compared to recombination should be more probable. And it should be many million cycles. It should be stable for many million cycles. It should not happen that it has absorbed light and after getting absorption, it is degrading or it is reacting in the excited state to the some semiconductor, or it is reacting to the some redox compound. Now, how do we prepare photoanode? So, as I said, this is deposit of layer TiO2. This is the fine details of thickness of FTO, and this is the you can say it is dipped in TiCl4 for half an hour, and then at 80 degrees centigrade, and after that it is annealed at 450 degrees centigrade. So this is the process by which these are prepared. Now, how to prepare platinum counter electrode? Because platinum is very expensive. You just don't evaporate platinum. So you have FTO material and FTO over FTO. One use the chloroplatinic acid, which decompose at 450 degrees centigrade and give a very thin layer of the platinum. These are some steps. How do we deposit TiO2 film by Dr. bleeding? Then after that, dye is coated by dipping it here. So after you see it was here, it was of white color. Then afterwards, it has, once you dip it inside this and place for several hours, predefined time. In that case, the color becomes like this, so that dye has actually loaded over the semiconductor. Then this is the preparation of counter electrode. Now here chloroplatinic acid mixed into propanol is placed here, and then it is fired at 450 degrees centigrade, as I written in the earlier slide, for 30 minutes. So this also, what you will get actually a substrate. One side is FTO, and over FTO you have now a very thin layer of the platinum. Here you have FTO. Over FTO, you have deposited TiO2 compact layer, and then TiO2 nanoparticle thin film deposited, and then you have placed it in the die. So you get now this. So now you have two part. One is this, one is this, and then you put one over the other, and in between just seal this by using a sealant and place a electrolyte solution of lithium iodide plus I2. So this will become your DSSC. And then take a contact from here, one contact from here, another contact from here. So this is a working dye-sensitized solar cell. Now, what are the issues with the DSSC? The issues are leakage and evaporation of liquid electrolyte. Liquid electrolyte which we are using here, this can actually leak. So that is a big issue. Electrolyte degrade also. That is an issue, and there is a hazardous nature of the components. And another is the cost, though we are using chloroplatinic acid, but still it is very expensive. So platinum cost is also high, and the stability is poor. So what is the possible solution is in place of the liquid electrolyte, now Hole transporter, which is solid actually. So solid state dye-sensitized solar cells these are called as solid state dye-sensitized solar cells, where in place of liquid electrolyte, you are using a solid electrolyte. And that is called as the solid Hole transporting material. And the one of the most famous material or most common material which is used as a Hole transport layer is the Spiro OMET TED. This is a very long, you can say, chemical formula for this, and the structure is same. So you have the TiO2 nanoparticle, and then in order to have this, you have deposited the TiO2 here. This works as ETL also because it's extracting electrons only, and then you have a transparent conducting oxide, that is FTU, and you have here. Then after Hole transporter material, you can directly use the metal electrodes, and the light should pass through this side. So the process is same. The working process will remain same. In place of earlier in the where the dye regeneration was taking place, in place of regeneration of dye, now the hole is directly transported from this to the dye to the metal electrode. Understood now? There was two steps now in the DSSC, where the hole was it was filled by the electrolyte component. Here you do not have electrolyte, but this hole can directly be transported to the outside metal using this material, Spiro. But this material itself is also unstable. Means it is also having instability issues. So in a solid dye-sensitized solar cell, liquid electrolyte is replaced with inorganic p-type semiconductor or organic hole conductor. In a few other cases, polymer electrolyte, where conduction is by ions, is used in place of the liquid electrolyte. These consist of mesoporous TiO2 with the monolayer of dye and hole conducting materials penetrating into pores of TiO2. So you have TiO2, you have different, you have deposited in such a way that there are a lot of pores there inside TiO2. So problems with solid state dye, this HTL material these are solid. It is very difficult to fill inside the pores, because in case of dye, it was very easy because it was liquid. You once put a photoanode inside the solution of dye, dye automatically reaches everywhere to deposit. But if you have a solid Hole transport layer, Hole transport material, how you will put inside pores? So that is another, that is one of the big issues. And then hole mobility in organic semiconductor is low as compared to electrolytes. Electrolytes, the conductivity was higher, but in this is these materials, solid hole transporting material, the conductivity is low. But you are getting your advantage is that you are removing a liquid part. And another issue is that recombination of conduction band electrons of TiO2 is higher compared to the electrolyte in case of the solid state electrolytes. So ideal hole transport material should have valence band slightly above the energy of of oxidized dye. This is the same principle as we discussed earlier also when we were explaining the hole transport materials, how they are made. And then some of the hole conducting materials that have been commonly used are, these are the some common, but spirometry is the most common materials. These are, but these are also used, but not very encouraging results. So with this, there comes perovskite solar cell. In perovskite solar cell, there is a slight difference uh, with the solid state dye sensitized solar cells, that in place of the absorber, you are using a perovskite material which absorbs the radiation. So all other things are slightly, you can say, comparable. I think we can stop here and then we'll continue in the next class. If you have any questions, please let me know. Go. So if there are no questions, then we stop here and see you on Wednesday. Thank you.